Okay, so let's continue with project. So this time we're going to measure really the thermal conductivities. So the real thing for our measurement could be a little bit different, because this time what we want to do is based on what we have done in the TCR measurement. So we want to scan the frequencies and get the 3 omega signals, because as we show over here. So we scan the frequencies and get the 3 omega signals, and the 3 omega signals can be converted directly into the kappa, right? So into the thermal conductivities. So the measurement can be done in the single temperatures, or it can be done in different temperatures. But this time I want to do a continuous scan. For example, I could flush with different samples. I can change a little bit and see if they're actually doing anything different, right? So this is my requirement. So I want to do to get the time versus thermal conductivity plot, all right? So instead of the traditionally the thermal conductivity versus the temperature plot. Obviously, I can do that, but like you can do it by yourself. It's very simple. So the thing I'm going to do is based on the materials we already done. So like this is the thing we already did, and now we want to change it a little bit and make it slightly different. Because here I want to do device settings. So like here we want to have the device, and then this is no longer the TCR heating TCR scanning settings. Instead, it probably becomes something I call it heating settings. Okay, heating settings. And I just, okay, so right now this is locked, so I want to unlock it, ungroup it. So it's going to be something like this. Okay. So we still have a potentiometer resistance, the signal amplitude, but this time usually we're using 5 volts, right? So because a higher voltage, and we still have the starting frequencies and end frequencies, and we have a the scanning point. And this time I want to add a little bit more. I want to add one more indicators. So that is how good the matching is. So I call it the remaining. I call it remain 1 omega. So that is called volts. Okay, that is called volts. Could push this a little bit far. And this plot, I'm going to change it as well. So I'm going to use this time a chart. No, sorry. So this time I'm using a graph instead of the XY. So it's going to be easier. So it's something like this. So I just want to make it big. Okay. So it's going to be a time versus my thermal conductivity, which is kappa. Okay. And this plot is really a means of the kappa versus time. Kappa over time. Okay, plot. Okay, fine. This is good enough. Okay, we have the set temperatures. I could have add one more. I could add a what I call it current temperature. All right, so current temperatures as Kelvin. The reason I'm doing this is because actually, like if you really have the instrument, you can read it from the instrument directly. But sometimes if you do it remotely, okay, you can absolutely out of the away from the instrument and doing it remotely. Just link it with the computer, right? So it's easier. And device settings, that's something we have a start temperatures. Actually, like this is no longer a start temperatures, but the set temperature, because we only have one temperatures, and we have a stabilizing time still. And we have the we don't have a temperature points, right? So we have a stabilizing, but this time we want to put the TCR in. So what is the derivative of the dr dt in terms of ohm? In terms of ohm over per Kelvin, right? So something like that. Okay, ohm per Kelvin. And we have a stabilizing time. We have this time I want to know, okay, because the device length is going to be needed. right? Okay, we said length, okay, in somewhere millimeters. So this one is going to be important. Okay, we have the stabilizing time in second, and dr/dt, and we're going to have the length, okay, something like this, and we're going to have temperatures, okay, set temperatures. We have a delta T, okay, so this is the same for everything. And here, this one is actually the measurement of the T, so like you're going to see what is the difference here. And other things, the front panels is the same, but here I want to make one more indicators like this, because sometimes like if I make a measurement, but like I make the potentiometer resistance is too small, that would means that means I cannot cancel the TCR. I cannot cancel the first omega signal, which is bad, right? So which is bad. So I want to make warning signs. So in case actually I have this situation, okay, so I can make the properties and change the on properties into the red. So just showing, okay, this is something really dangerous. Okay, so something like really dangerous. Okay, so like if it's not on, so like if it's off, we're just using the gray. Okay, fine. Okay, so I want to put this indicators over here. So in case there is anything wrong, okay, I could know this is the case, right? So this is something I change a little bit, because you have to take the consideration, like people using it is going to be making mistakes. So they're going to make mistakes, but as a programmers, we know how to do that. So, and because this is a warning signs, so at the back, so I really need to do is change this this sub VI, because we said the sub VI is last time we measure it, but there is no warnings. Okay, so like when the ratio put it in is greater, okay, it's greater than 1 or equals to 1, so that is going to make a trunk, like they're going to round it to between like 0 to 1, but there is no warning for that. So I want to add one more thing here. Okay, add one more thing here. So just to add a comparisons. Okay, add a comparisons. Says if this is greater, greater or equal to 1. Okay, create it constant. Okay, if this is greater or equals to something like 0.9998, if this is actually over it, so this is going to make a warning sign. Okay, so like make indicators here. Okay, so this is something I call it warning. Okay, so like warning. Okay, like warning. Okay, so this is the warning one. Okay, a warning one, and for here, I would need terminals. Add one more terminals, and this terminals. Wire it here. Okay, so that's fine. Okay, so that's fine. I can save it. Okay, and close it. Okay, now this one has to be relink, and now they have one more warning signs over here. So this is how it actually works. Okay. And I say a kappa over time, so this one is we're to do it later, okay? And in this case, because there is no time really in, so we don't need to set this time anymore, okay? So what I'm going to do is essentially I'm going to take this, but remove everything over here. So everything has to be removed down the way. And there is a loop. Remember, there is a loop, and this is a for loop. So if you have a temperature scanning, you need this loop. But in this case, we don't need this loop. So what I'm going to do is I'm going to remove. Okay, I'm going to remove this loop. I'm going to remove this loop. So I'm going to remove for loop. So this for loop is gone. All right. So again, everything else is the same. I just based on this, just continue doing it. Okay, just preparing. So here, this is basically it's a process of preparing stuff, right? So preparing stuff. Actually, like I don't need this one. So this is actually how I save the data. So like the saving data one is going to be different. So I'm going to remove this one. So like later on, actually going to become different. Okay, it's going to be different. Okay. So everything is going to be quite different for now, okay? And actually this thing is also going to be different, okay? So I just close them for this moment. And now there is a case, right? So this is actually we have a case structure. We can add a case before. So this case before, I will call it preparation steps, okay? I call it preparation steps. Basically everything in the loop. This time I will put everything in the loop. Right, everything is a loop. It's just like move this a little bit to the side so I get more space, and I could just like basically move this in. Okay, I could, or actually I could make this a little bit more space. I make more space here, and I could move this in, okay, and I can move this, okay, stuff also. Oh, right. Okay, I can move this stuff, everything related here. Okay, I'll move it inside. Right, so this is a thing. Sometimes it's a good practice to do this because you're going to see how. Okay, so I press Ctrl B, so like remove all the warning signs. Okay, remove all the broken wires because I'm going to rewire everything. Okay, so now this step becomes a step like preparation. Okay, so I get all the instrument ready. Okay, so here again, so like harmonic one, sensitivities, and putting the amplitude in. So this amplitude is high, and again, and everything is it's just as what I did previously. Okay, so this is where the Visa DAC. Okay, Visa DAC, I would I'll put it a little bit down, so it's just giving me a little bit more space. So more space to do. All right. Okay. So as I said, this step is initialize. Okay. I said initialize instrument. Okay. Instrument. Okay. And then in this step, it's what I call the it's what I call the set temperature. And in this one is actually weight stabilized. Okay, so that's fine. Everything goes here. That's the same, right? So this is really the same. This time I could do a little bit different. Okay, I could do a little bit different. So it will be slightly better. Okay, slightly better because in here, what it does is actually it's check whether the temperature reach the temperatures or within the temperature limits, and then it's just keep. If it is, it's just go. But there is one problem, like you can have a temperature it's reach the temperatures, but they're actually fluctuating. So if they're actually fluctuating, it's not good. You probably wants to wait until it's actually stabilized a little bit, right? So it's not go as much. So that is something like it's different. So in order to do that, okay, so I do it quick. Okay, I already programmed it, so I'm going to just copy it here, so you can see how it actually is. Okay, it's pretty simple actually. If you read it properly. Okay, so I give it a little bit of space so you can see clearly. So what these subway this block is actually doing is this. Okay, it's this. So let's just link it so you can see it clearly. Okay, just put it here. I put it here. I put it. Okay, so what it does is it actually change the current temperatures, right? So it's actually have the current temperatures Okay, so let me just close this one for now, and I have the set temperature, I have the delta T. I just move it everything here so you see. So okay, we'll have current temperatures, and so it's actually having current temperature 2 or something like that. So I can move it down here. So I can rearrange it later, but essentially it's something like this. So I could have, okay, a current temperature is read. So this is actually give me what is the current temperature is, and I could subtract it with the set temperature. Okay, so this is a my set. Where is my set temperature? So my set temperature is here. Okay, so this one is my set temperature, and this set temperature was initialized in here. So this is easier. So I just put it here so you can see clearly. So my set. So I can wire the set temperature down here. So if the set temperature is minus the current temperature, and basically I get the numbers, and the difference is basically the delta T, and I could take the derivatives, basically, well, not take derivative. I could analyze it, look at what is the mean values, and look at what is the absolute values of the fluctuation. And if the fluctuation is small, then that means it's good. So I look at the so this is basically called standard deviation or variance. So this is actually inside the probabilities, which is previously we were using mean, and this time we're using the standard deviation and variance. Okay, so this is actually the same, but they actually give us a little bit more. So this time the difference, the criteria is the difference is less than 0.01, and the standard deviation is less than 0.01, so like 0.1 and 0.01. Okay, so that means it's really stabilized. Okay, for example, oh sorry, I forgot to actually having the delta T as the absolute values. Sorry, so it's actually need to take the absolute values. Okay, takes the absolute values. Okay. Okay, I forgot to take the absolute values. Okay, so the absolute values of the difference is less than 0.1, and it's less than this, so this is going to be good. All right. Okay, so this is basically checking what is the temperatures, okay, current temperatures, and then we have another checking temperatures, which is here. We're going to use it later. Okay, so this current temperature is going to be used later. Okay, or we change it to this as a measurement we say measurement temperature, so it's not going to be confusing. Because previously we actually do the scanning from a start frequency for low frequencies to end the frequencies by looking at what is the difference of the omega of the 1 omega. So this time actually we don't need these much. Okay, we don't need to do that much, but instead we're actually only going to do the matching the resistance at the starting point, at the starting frequency. So because it's quicker and easier, all right? So how to do that? So like that means I can basically remove everything from here. So there is no point to scan anymore. Okay, and for here, so this is actually my scanning point for start and ending points. Actually, I don't need it. So in this time, but like in order to match, I still want to create some kind of a loop to basically create a constant. All right, so this constant is basically, let's say, I just do 10. Okay, it's a 10 times of the basically it's repeated to take the measurement for 10 times more, and then basically getting some numbers. All right, so this is fine. So it's these things is going to take the measurement of the 1 omega, okay, 1 omega signals. Okay, it's going to take the measurement of the 1 omega and then at the frequencies of my starting frequency. So this one, so for starting frequency is still needed. So I don't need this one, but I just put it in the starting frequencies at this. So it actually goes in like this. So it's going to make a measurement of the channel A and channel A minus B at the frequencies of the starting frequency, and then do the measurement for 10 times, and then take a mean values and getting the potentiometer resistance and the sample resistance. Right. So this is something like actually I need. Right. So I would need this for the real measurement. Okay, I don't need to take the measurement of the temperature at this moment. Okay, so because this is just a scanning steps, so I don't need that. Okay, later, like I'm going to make a measurement of the temperature later, but not at this moment. Okay, the next thing here is I have this data. This R, and I have the A and have the B, but now I could calculate what is the ratio would be needed, right? So I have the ratio, because this is R, this is A, this is channel A, this is channel B, and A divided by B, okay, is basically my my ratio, right? So I would need the ratio, what is this one? I would need this ratio to be the I would need this ratio to be somewhere like here. So A divided by B. So this guy, okay, that's already on, so I don't need this one. But I would need to have this guy. Okay, I've updated my DAG with a new number. Right, so with a new number, and this number is going to be very important. So this number is very important. This number is going to be from here all the way down here. So after this should give me a pretty good match already. All right, should give me a pretty good match already. But at the same time, I want to have, because I have warnings. So if they cannot match, okay, if they cannot match, it's going to send out a warning message. Okay, it's going to send out a warning message. Okay, so this is a warning message it's actually sending out. Okay, I could put it somewhere here so it's easier to see. Okay, oops. All right. So the next one is actually I'm going to switch to the what we call a 3 omega measurement. Okay, so let's switch to the 3 omega. So this is actually something like I could close this. Oops. Let me disconnect this one first. Just move this away. It's actually I need much more space to do that, because this time is actually a time for switching to the 3 omega measurement. Okay, for 3 omegas, so what I need to do is basically, let's say, okay, it's already off, so I'm going to put some kind of command in. So this command is changing the switch to harmonics 3, and then press the auto gain again, because the auto gain is important, because after the switch to the third harmonic, the signal is going to be much smaller. Okay, so this one, I guess, is going to take some time to finish. Okay, this one is going to take some time to do. And now, once it's actually coming out, it's already A minus B, so it's going to have a harmonics 3 and A minus B. And let's say this one took, let's say, give them like a 3 seconds to finish. Okay, so this one is what I call the switch to 3 omega. Switch to 3 omega. And then let's continue going. Okay, let's continue to go. Let's continue going. And let's just keep going for the next one. So the next one is really do the 3 omega measurement, right? So it's really make the 3 omega measurement. Here, there is something like we need to calculate. That is basically what is the scanning again. So this time, I want to do a little bit things as the mathematics. Okay, so this is actually the same as what we did previously, exponential, because it's going to be exponential one. So, but this time I'm using a natural log. The reason I'm using the natural log is actually because natural log is going to be used in the final calculations. So I could just calculate it now. So it's not going to make too much difference. All right, it's not going to make too much difference here. All right, so fine. So this is basically a natural log of 2 things, and then I have several data points, and I could do the -1, so decrease by 1, and then I could take the divider. Okay. Oh, sorry, it's actually needs to subtract, right? So I need to subtract A minus B and divide it by this guy. So this is my intervals, right? So this is my intervals, and this is my points. And then I'm going to scan everything, right? So this is actually going to scan. Okay, so like add a frame after. Okay, so this is a frame is really going to do the job. It's going to really do the job. That is going to scan the frequencies. Okay. In order to do the scanning, it's also pretty straightforward, right? So once I already have this guys, so actually, like it just the only thing you do is simply just scanning the different frequencies. So this is actually the same. Actually, we did it last time. Oh, sorry. So that actually we did it last time. So actually, like I should use a for loop. So for loop. So a for loop goes in here, And in the for loop, I would have how many data points in it. So how many data points? Move it a little bit here. I could have how many data points here, and I could have what is the intervals, and I could have the multiplier. So what is the number of the it's actually just like this, right? So it's the same thing as what I did last time in the previous run. So this is a derivatives, this is a logarithm of that, and this is multiplied by the n-1, so this is actually that. And then I have a starting point, which is equals to this. This starting point is add, so basically I add it like this, so let's go here. So this frequencies is what the real frequency exponential of that real frequencies, and I took the exponential, and then I took a round to nearest integers. Okay, so this is the integer numbers, and then I basically convert this into a string, and then change it into the frequencies, which is the same as what I did last time. So basically I copy the what the actual last time is, so we did, right? So here, okay, so that's fine. So frequencies of this and semi-common. Okay, so that's done. With that, actually, like the next thing would be the data write of the copy, right? So it's basically here. So I would just copy as much as possible. Okay, I would copy as much as possible. I would copy these. I would copy this. So this is fitting here, and this is intervals. This is intervals. Okay, well, what is this one? So this is nothing here. And so now it's actually third harmonics, and actually I wait for 100 seconds, and then output 1 and takes the measurement and coming out and get the data, right? So then after it, probably I could wait a little bit more. Okay, I could wait a little bit more and take another measurement. Okay, take a little bit more waitings and take another measurement. So this waiting it's probably not needed, but like sometimes I still put it, so in case there is something wrong. So like if it's really small, it doesn't affect our speed, because if we want to further increase, we can later on change the numbers into 0 or something, so it becomes much faster, right? So that will be it. Okay, so after this loop, okay, after this loop, so this is going to give a series of a 3 omega signal, right? So a series of 3 omega signals. So some of them is relevant, okay, or all of them is very relevant, or the slope of the frequencies is going to be relevant to the it's going to be relevant to the thermal conductivities of the sample, right? Okay, done. Okay, so that's fine. Output 1, so this is x, and everything is the same. And I'm getting this one, these numbers, and the slope I'm going to take. So this is something like the slope I'm going to take is actually the natural log of the frequency, which is actually here. So this is this guy. So this is the natural log of the frequencies with the 3 omega signal, right? So this is output. I put it here, okay. And this is the natural log of the frequencies. So I could put it here, right? So it's like two things, and I want to measure what is the slope of that, right? So I want to measure the slope. So the slope is actually in the mathematics fitting and the linear fit. Okay, so in linear fit. So in the linear fit, so they actually have a bunch of things you can see over here. So they actually have x and y. So the first one is y. Y is in our case is actually our stereo omega signal. Okay, the x is the logarithm of the frequency. Okay, so once they get this, so this number is a slope, and this slope, if we actually look at the equations, so this would be the slope, but like this slope is really like converted to delta t. So you can change this a little bit, so it becomes a v cubic over the r squared 4 pi l, something like that, right? So it's r squared. So then I want to get a little bit conversions. So how to get the conversion? So I already did that. So it's actually like this slope multiplied by some kind of ratios, and this ratio would be the potentiometer resistance. This is basically the ratio. This is a sample resistance. So if I have a sample resistance, and the sample resistance take the square, so that means the sample resistance square by a 4 times the sample square constant is a 4, and multiplied by the number of numerical plates and some constant, and it's a pi, and 4 pi, and the length of our stuff. Where is the length? The length. So this is a length. The length of that. So this is a really, because here there is it's actually inverted. So like it's actually inverted. That means it's 1 over this number, all right? So because actually, if you look at the equation, so r is actually on the denominators. Okay, it's on the denominators. So I'm changing it to invert. Okay, and then this number has to multiply it by the another numbers. So that is our TCR numbers. So where is the TCR? Oh, so the TCR is actually going to be the double precision numbers multiplied by the something. Okay, so I could also get in the mathematics compound. Okay, so again, it's going to be the change mode at multiply. So there's going to be several things. So in this time, actually, is a cubic of the a values. Okay, of the a values. So cube of the a values. A value is actually here. So this is the a. A is here. So a is this guy. So this is a first harmonic voltage. First harmonic voltage. It's over here. So the first harmonic voltage up here. So it actually needs to be done 3 times. So because it's a cube, right? It's a cubic. It's a cubic of that multiplied by the TCR, multiplied by the TCR values. And then the final thing is divided by this number, so or multiplied by the reverse of this number. So this becomes a ratio. Okay, so this is a ratio. So I could write it here. So this is a calculate conversion ratio. Okay, something like that. All right. So this ratio multiplied by the slope is equals to the kappa, the thermal conductivity, right? So that's fine. Okay, that's good. So I would need some kind of a multiplier. Okay, so this is a multiplied. So best linear fit is slope. The slope multiplied by this guy. Okay, so actually I can move it a little bit up, so it's not going to occupy too much space. All right, good. Okay, so this is all actually I would be pretty much need, okay, for this. So after this, I getting the kappa, the thermal conductivities of my device at that moment. And again, as I said, I want to scan this over time. So like basically I want to loop it, right? So that means I'm going to create a while loop. Okay, so this while loop is going to be over everything, right? So this is while loop is going to be over everything. And this is going to be somewhere, let's say here. I want to put it here. Okay, and this one is a stop button. So this stop button is useful because this means actually I'm going to stop measurement. All right, so this is actually pretty useful. Let's say stop measurement, something like that. Okay. View as icons. Okay, good. And this becomes small, and this is my kappa, and I'm going to plot that, and also I'm going to plot other things. Because again, I want to record everything, so I'm going to again, as what I did last time, build array. Okay, not build array. Sorry, it's initialize array. Initialize array. Build array can be used later. Initialize array. So this is actually going to be used as a constant to actually save my data. Okay, it's actually used to save my data. And how many data I want to save? I want to save, number one is the kappa, obviously. Number two is what is the remaining the sample resistance and the remaining resistance. Okay, so like where after I forgot to record what is remaining resistance here. So actually like this one should be recorded. So that means actually I need to add one before. Okay, before everything's. Okay, that has to be added before the before this stuff. So what is really doing is so I just want to make a measurement again. So just make a measurement of the take a measurement of the first harmonic again. So I don't need an auto gain. So I want to I do need an auto gain because then after this one, its gain is actually becomes smaller. So I can auto gain it and make a measurement of the take a measurement of the A minus B. Okay, take a measurement of A minus B. It's this stuff. Auto gain. Let's say this auto gain could take a while. Okay, that could take let's say 2 seconds or something. 2 seconds or something. And okay, this is done. So going in here, and they're going to make a measurement, and this is A minus B. Okay, this one is basically the remains of A minus B. Actually, the remains 1 omega V is quite important because if they actually is too big, that means my program or my measurement or something somewhere is broken, right? So it's not right. Somewhere is wrong. So this one is really needed. So remaining 1 omega. So this is after coding, and this remaining one is needed. Okay, I would record this one. I would record how many remains down here there. And okay, so this is how actually I'm going to build an array based on this. Okay, so this is arrays. Okay, enable a shifting resistor. Okay, and here shift the resistor, registers, and here I think 4 would be enough. I think. No, if not enough, like I add more, definitely. Okay, I can add one more. Okay, good. So this is everything I'm putting in. Okay, everything I put it in here. And the first one I think I'm going to do is a temperature, right? So because temperature is definitely needed. So what is the current temperatures? Okay, I just want to check, right? So sometimes if it's wrong, so there is problems. Okay, so the key, not key sleep. So lecture and data and read. Okay, so the read data. Okay, sensor. Okay, and this is going. Okay, this is going. This is going. Okay, fine. Cool. How many kelvins it's actually going through, and what is the current temperatures? And I'm going to build this array. Okay, fine. This array is in, and the second one is actually what is the so I just keep adding this. Okay, so I just keep adding put OR. So the last one is basically my kappa. The last one is my kappa, and okay, the front one is what is the remaining voltage, 1 omega voltage. Should be small, this one, and wants to know what is the resistance, because the sample resistance of here. So sample resistance, you can see it actually goes here. So I could put the sample resistance array down here, right? So this actually copy everything. Okay. So this is probably all actually I would be interested to do. Okay, I will be interested to finish all of these. Okay. And then it's pretty much almost done. So this is actually going to scan, or I just put here. This is called scan 3 omega signal at all frequency. Right? So frequency and calculate kappa. All right. So this is something like really important. Okay, so this is really doing the job. But actually, I can see this is I could put 100 millisecond or 50 milliseconds. If I actually have a 15 or 20 points, so like each data measurement is probably takes around 2 seconds or so. So 2 seconds I could get the thermal conductivity. So it's good. I could further increase, but at this moment I think it's fine. All right. So the next thing is I could just move this a little bit hot. Okay, is so the next stuff I want to do is a plot, right? So I forgot to plot because actually I have this one. So it's actually a kappa over time, right? So I want to build a time slot, right? So time slot. Build a time slot to actually plot this over here. So actually it's because it's actually scanning inside, right? So it's actually scanning inside, so it's probably better to let this whole thing inside as well, because they're actually getting one data point really quickly. So in here, what I'm going to do, so this one is actually the kappa, right? So this one is kappa. So I'm going to use something called a waveform. It's actually this this guy, this is a waveform plot. So this is so it actually takes a waveform. So actually it needs to go waveform, and it's called blah blah blah. Build a waveform. Okay. So you build a waveform out of this thing. Okay. Out of this string data, and this data can be plotted directly. Okay. Into this whole thing. Okay. This would be probably it, and after it's done, I think it's time to save and close. Right, so add a frame after. Add a frame after. So add a frame after. So this one, it's going to be a time of savings and closing. So to save data, it's pretty much the same things as what we did previously. So you just build everything, right? So you just build everything together. Okay, just build everything, and then this 2D data getting. Okay, so if there is a already that name is there, so it's going to make a new name for you, a new file for you. Okay, default is this one, so we can create a constant, and this constant is force. So that means like if you you don't have the risk to overwrite your real valuable data, right? And then this one probably move a little bit down, so just leave a little bit space. Okay. And this I want to close everything. So in order to close the whole system, I would do a harmonic 1. So I would change the harmonic to 1, and I would do the sense. I would change the sense to 26, and move to the channel A frequency 1 kilohertz and something like that. Yeah. So this is how I let the locking amplifier settle over there. Right. So it's going to stay at certain locations, just like that. Good. This is fine. And here, this guy needs to be closed. So the DAG needs to be closed as well. Okay, the DAG can be closed. The DAG can be closed. And finally, it's the locking amp. It's a temperature controller. So like I'll move it inside, so it'll be easier. It's going to be closed. All right. So you can see actually this becomes arrows. So there is no problems to run. Oh, I forgot to actually took the measurement. So the measurement temperatures is actually going to be constantly checking. So whenever you have this one, it's going to be added. Okay. So this would be it. So I have everything is on. So it should be able to plot everything as needed. Okay. So finally I could rearrange this guy. Okay, a little bit. So make them a little bit nicer. Okay, a little bit nicer. Device settings, something like that. All right, so it's not super important, but it's just make it a little bit good looking. Okay, and then this is it. So this would be the once you press start, so they're going to measure the thermal conductivity over time, and you can see they're actually going to plot over here supposedly. And then when you are done, like you click stop, and then they're going to save into the folders you actually into the files you actually say over here.